SMT approach. So these are the main two research questions that I want to address in this talk today. And the main objective, as I have discussed it here in the first slide, so I want to present what our research group has done in the past, what are doing nowadays in terms of software verification, also what you plan to do as the next step. We have worked over the last decade developing software model checking techniques, include verification strategies based on bound model checking, k-induction, incremental BMC, exploiting SAT and SMT solvers as a backend for those verification strategies. And then in order to handle the case of undecidability when you verify programs, so we know that, well, BMC is a quite powerful technique. So bound model check analyzes bounded program runs with the goal that can achieve decidability. The verification platform that we have developed and worked over the last year, so we offer a bounded model checking analysis for programs. We have also seen a revolution, right, in terms of SAT solving. So nowadays, SAT solvers can handle formulas with millions of propositional variables. And then the SAT solver is the main technology, right, that's used behind the SMT solvers engines. And then if you want to take advantage of high-level information, right, that you have in the program, we can use the background theories of the SMT solvers so that you can exploit better encodings using the word-level theories, right? Like you can exploit theories like the theory of arrays, linear integer and real arithmetic, theory of bit vectors, and so on. And another thing that also helps us when verify programs is about invariant inference, right? So you can get the program, and then from that program, we can actually make use of abstract interpretation techniques to compute abstract domains, for example, based on intervals, octagons, polyhedral. And then we can use those invariants together with induction techniques, right? So our research group has also developed over the last year k-induction proof rule, and then with those invariants that you can infer from the program, so they can help us quite a lot to prove more programs actually than plain BMC, which plain BMC is quite focused on falsifying properties in programs. So that's the objective of this talk. So I start here with the SAT solver as the enabling technology, right? So we have seen that, well, we have seen a major breakthrough in SAT solving early 90s with the Z-SHAF and GRASP. And then over the decades, we have seen a substantial improvement of those SAT solvers employing techniques like propagation, conflict clause, and no chronological backtracking. And then, that liberates applications related, for example, to quality tests, program analysis, equivalence checking, and quite recently, so we have also seen the application of synthesis, like via the CIDS, the counterexample guided inductive synthesis, where the SAT solvers enabled such an application in formal methods. We have also annually a competition, right? The SAT competition. And then in the last edition of the SAT competition, we also started seeing parallel SAT solvers that they consistently outperform the sequential SAT solvers. So by exploiting the multi-core clusters and so on, right? So you can even create even larger formulas that can be solved nowadays by those SAT solvers. So the application, that area is growing, is still growing. And here I start with the basics, right? So about BMC of software. So we model a program as a state transition system. And then that state transition system, so you have the initial state, you have the set of states, you have the transitions that can tell me how I can go from one state to another. And then each state, I have the information about the program counter, in which location I am in the program, and also the program variables, the local and global variables that I have in the program. And then we derive that transition system from the control flow graph. We also, when you build that control flow graph, you can automatically instrument that control flow graph with language specific properties, like, for example, array out of bounds, division by zero, arithmetic overflow. And then you add those saved properties as extra nodes to the control flow graph. And then we unfold the program up to a given bound, right? So when you unfold the program to a given bound, we exploit several compiler techniques, right? Like constant propagation. When you assign a constant to a variable, so you can propagate that throughout the control flow of the program. For substitution, so when you are performing the symbolic execution of the program, you also realize that, well, there are expressions that are repeated, and then we save those expressions in the cache, and then retrieve from the cache. Especially when you are producing during the symbolic execution, the SSA, the static single assigned form. And then we also detect unreachable code, right, when you unfold the program. And then there are detect nodes, basic blocks that are unreachable. And that helps quite a lot to reduce the size of the formula that we give to the solver. And then when you do this optimization, I mean, when we symbolically execute the program and then apply those techniques from the compiler domain, so we generate the SSA, right, the static single assigned form. And then the common property in SSA that each variable is assigning exactly once, right? And then from the SSA, so we produce two sets of formulas, C and P, right? Where C is the constraints, the assignments that I have in the program, and P are the properties that I want to check. And then also extract the C and P. I'm not monitoring here the chat, but can. Okay, since are you trying to exhaust all outcomes of find the entire sample space using fundamental principle of counting? So with BMC, what we're trying to do is essentially to find, we're exhaustive up to the bound K, right? So later I'm gonna show a technique that you can actually prove the correctness for any value of K, right? But it's exhaustive up to the bound K here, that technique.
Okay, so okay. Yeah, I got it.
Yeah, okay, good. And then we can, well, there are a variety of SMT solvers, right, that are available as off the shelf. We can also select which theories you want to verify the program. For example, the verification platform that we developed, we essentially have two main theories. That the theory of bit vectors, right? So that models precisely the semantics of the program. Or you can also model the program variables as integers and reals from the mathematical domain. Okay, so these are the two main theories that you can select when you model check programs. And then we build a formula, right? That is the conjunction between the constraints and the negation of the properties. And then we want to check for the satisfiability, right? So in this particular technique, what we want to do is we want to find property violations up to the bound K. Okay, so I'm going to show, I have prepared one example here just to give an intuition of how we verify programs with this technique here. So let me start my presentation, then open here Visual Studio. Okay, and here Visual Studio, this example is the one that's in my slides. We have here the main function, right? That is the get password. The user is going to type the password, and then we are going to check if the password matches what we have stored here. Okay, so then it can give access granted or access denied. And then if you look at the get passwords, what you do, you declare buffer, right? And then you do a string comparison here. So that string comparison will be with, we are going to compare that string with SMT. And then I have different versions of how you can get the characters that were typed by the user. Okay, the first version, so that is quite well known, so that have the gets, right, which we know that's an unsafe function. And then when you try to verify programs, the programs, they use libraries, okay? And then when you do model checking of code, of software, we have to consider those libraries. And then the way that you can consider those libraries in our verification engine, we have to build operational models, okay? What are those operational models? They essentially describe the pre and post conditions of each function. And then you also have some code that simulate the behavior, right, of the function. And why we build those operational models? Because we start from the principle that, well, the library is correct. And then what I want to do is to verify programs that use those libraries, okay? That's why you create that operational model and then you instrument with the pre and post conditions. And then in this particular case, just to give a bit of the flavor how it works when you do the instrumentation, right? So for the gets function here, so I get the specification of the gets function, then it tells me that, well, the user can type any number of elements, right? The password, so I can model that variable here size as a non-deterministic unsigned integer. Okay, so then the model check is going to check the entire state space considering the intervals for the unsigned integer for that particular architecture, right? So if 16, 32, or 64 bits. And then I have a loop where I'm going to store on each position of my buffer the character that the user is going to type. And then you have another non-deterministic function here. That's know that SHA. That's gonna provide, well, the user can type any unsigned SHA as part of the password, right? And then so those that model is usually embedded into the library that goes with the implementation of the model checker, right? So if you consider model checks, let me say, like CBMC, SBMC, CPA checker, SMAC, and etc. So all those model checkers, they have some they have the built-in libraries, the implementation of those built-in libraries with that style of the operational model that you can instrument the library with the pre and post conditions. And then if you call here the model checker, so I'm gonna call SPMC on this example. That's motivate example, right? And then I'm gonna call here incremental PMC, okay? And then I can also disable here some simplification that do like for the slicing. And then if I model check this program here, so you can see that, well, what's gonna happen, as you can see here in the summary. So we have produced here 24 verification conditions from this program. Where we have simplified most of them, and then just 3 of them were given to the SMT solver. And then when you build the SMT formula, so here you use the bit vector floating point arithmetic, okay? And then in this particular case, you have used the SMT solver Z3 to check the formula. And then when you start this verification process, so you get the program, and then from the program, we build the AST. So in our particular case, we use Clang, okay? For the C and C++ front end, we have also recently developed Solidity for smart contracts front end as well. And it is the same. So you get the program, then goes the AST, the abstract syntax tree. And then for the AST, we build, we convert this to our intermediate representation. That's a go-to language. And then from that go-to language, we build the control flow graph, and then we symbolically execute that control flow graph to produce the SSCA. And then you extract that 2 sets of formulas C and P, and then choose the theory that are going to check that formula. In this case, we have to choose a bit factor floating point theory, okay? And then give this to the solver, so the solver finds that the formula is satisfiable, and then gives me the count example. And then you extract that model from the SMT solver, and then you build this count example. That's actually, as you can see, as I have discussed it here, it's a state transition system. So you can see the state 1, 2, 3, 4, and so on. We can see also some internal variables that we have in our model, right? For example, we we have variables here that allows us to check the dynamic memory objects that we have in the program, right? Also about the round moting when you talk about floating point and so on. Also, we have also support for multi-threaded, right? So then you also keep tracking of the number of total threads that have the program, the threads that are running, and so on. And then comes the part of the program that have the buff, right? So in this particular case, we have considered that, well, the user has provided a password with 7 characters. And then here you have the content of each position that I'm going to store in the buffer, right? For position 0, 1, 2, 3, and so on. And then says that we have found a array bounds violated for this case, which was expected since we have used the unsafe function, right? Is there any concept of a free variable here? Yes, we do have the concept of free variable. So you can actually create that variable. And then if you don't place any constraint, right, in that variable, like is the case of the node that, right? Let me say that we have X, assign a node that. And then if you don't place any constraint in X, right, so that X can assume any value given the type of the node that that I have chosen in that assignment. Okay. Did I answer your question, Sudakshina?
But there is a concept, right? So free variable is, there must be some constant. It must be an integer or character, or some constant must be there, right?
Yeah. If you
So
don't have any constraint or any constraint with that variable, so that's a free variable.
Okay, so do you mean integer linear constants?
Yeah, could be integer linear constraints and also in bit vectors as well.
Okay.
Okay.
Thank you.
Good. Yeah. And then, well, as you know, so if you want to solve this problem of array bounds violation, actually can use a safe version of gets, right? That's fgets. And then if you use fgets, I'll just remove here that no slice. So then you can get here verification successful from the verification engine. Okay. You can also see that, well, we have used the incremental BMC, right? But well, Lucas, you have just described here the bound model check technique. Yeah, the bound model check. So we specify the bound, right? That we're going to unfold the program. But you can do also it incrementally. That, well, we can go 1 by 1 or 2 by 2. So that's configurable, right, in the verification platform. And then you can also exploit incremental BMC, incremental SMT solving, right? So that you can learn from one step to the other, right? About the VCs that you check. We have also that feature enabled in our verification engine. And then most SMT solvers, they support incremental SMT solving. But from our experience, incremental SMT solving use the push and pop mechanisms available in SMT solvers. So in practice, they don't perform very well. And then in this case, so you can either choose, can do incremental BMC just increment K, or you can also enable incremental SMT solving as well. Okay, good. So let me go back here to the presentation. I don't know if you have questions about this running example. Oh, so let me move forward. And then, so we have evaluated this technique over a large set of benchmarks, in particular for embedded software verification. And then we have collected here a set of public benchmarks that contains applications related, for example, to automotive and control, Fourier transform, JPEG encoding, signal processing, and so on. And we have also evaluated some model checkers, right, that are popular in the field, like TLS, CBMC, CPA checker, DFK, which exploits invariant inference based on polyhedra. And then this technique here, so in that evaluation that we implement in the tool that's called ESPMC, right, which ESPMC is part of the family of the CProver framework. And those that know the CProver framework, we have the CBMC, we have the TLS. Evaluation here, so ESPMC achieved the second place in that evaluation, consider those embedded software benchmarks. And one thing, as you can see here, so the best evaluation was for 2LS. Okay, so 2LS is also built on top of the cProver framework, and they use k-induction and invariant inference in order to handle loops in the program, right? So then we have realized, okay, so BMC technique is quite strong, but when you have programs with loops, the technique struggles, right? And then the second step of our research was essentially to go further with the BMC technique, right? So that you can try to verify programs with loops. So consider here this loop, this program that we have the while, and then while we have y is smaller than 1000, and then we have a no determinism here in the loop, right? That know that int can return any integer number, and then inside the loop, so we just increment x and y, and then you check if x is greater or equal than y, okay? So then comes the question here. So does this program terminate? In a close, a quick spectrum, it's tricky, right, to answer that question. I'm going again, just use, I have implemented these here, and then I put in Visual Studio, that particular example. Let me consider here, I'm gonna run ESPMC over that example here. Let me call ESPMC contractor. And then, so you keep running here while I give the talk, and then I come back here later for this example. Then the next step of our research was, well, okay, so let's try to see if we can do better with BMC in terms of programs that contains loops, right? And then we started investigating a technique that's called contractors, that comes from CSP, the constraint satisfaction problem. So and then applying BMC using table methods via contractors, just to give you here an overview of how it works. So the first step of that approach, we aim to analyzing tables and properties. So consider here that I have this program with X and Y, okay? And then I have some constraints over the values that I have over X and Y, and then I check if X is greater or equal than Y. And then here we can actually create, well, deploy abstract interpretation. In particular, can build an abstract domain based on intervals, okay, to compute what would be the intervals for X and Y. And then you convert these, the problem into a CSP, the constraint satisfaction problem, that have the variables, domains, and constraints. So the domain X is going to vary from 20 to 30, and Y from 0 to 30. And then the constraint is essentially here that the assert that I have here. And then I'm going to do Y minus X is smaller or equal than 0. So you convert this to a CSP, and then you apply the contractors, right? So we can visualize here our program, right, in terms of the state space, that we have the variable X and Y that we have computed in the intervals, use abstract interpretation, which is a very common technique and very powerful technique to verify programs, right? And then what to do, so then we apply the contractors from CSP, right? So we have the operators of forward step and backward step in order to prune the state space exploration. Then when you apply those operators here of the forward and backward, we conclude the following. So we have the red area, right? So the red area is the area that holds, okay? And then the green area is something that we don't know if the property is going to hold or not for the green area, right? And then when I apply the contractor, what's gonna do is essentially this, right? So you have that search space here, as you can see in green. And then after you apply the contractor, what remains from the search space is essentially the orange area when you apply that forward and backward contractor. And then based on this information, so we actually add that constraint also to the program. In this particular case, is going to be Y is smaller or equal than 30 and Y greater or equal than 20. And then when we add this constraint here to the program, so and then give to the model checker, in particular for BMC, BMC is going to check just the orange area. So that's going to reduce quite a lot the search space. Let me go back to the run example, right? So I have just run here, look. The SMT solver, right? Our decision procedure took 112 seconds, right? And in total, it was 118 seconds to verify this program. And then I did my homework, right, to get this program and then apply that technique of CSP via contractors. And then we can add that as an assuming, right, to reduce here the search space exploration. And then if you run again this program, right, so that's going to unfold that loop 1,000 times. But the formula that was given, right, to the solver, the region that should perform the search is much smaller, right? So now you can actually verify this program in less than 7 seconds. Okay. We have evaluated this approach on some benchmarks from SVComp. So you can see here the result of this evaluation, right?
Lucas, a question?
Yeah, okay.
On the previous slide, so how did, I mean, so this assumes, one question is, how did you know what assumes to add, and you know, how do you do that automatically?
Yeah, so then we use CSP solver, right? So the first step is that, well, we have, we use abstract interpretation to compute intervals. In our verification platform, we build a dependency graph, right? And then from that dependency graph, we build intervals. So initially, the intervals for the variable we set to infinite, right? And then as you start walking through the graph, right, and then see the assignments, so you start compute what would be the maximum and minimum value for those variables. You use the abstract interpretation technique, which is standard in the literature. And then you can use, for example, even other abstract interpretation frameworks like FramaC. Right, we use quite a lot in our research group, the FramaC, to compute intervals. That's the first step. We deploy those techniques of abstract interpretation to compute the intervals. Okay. And Lucas, can you do it automatically? Yes. So FramaC does it automatically. Also in our verification framework, we do it automatically. And then once you build those intervals, we automatically add those intervals as assuming, right, in the code. So we have an option that if you choose minus interval analysis, we're going to get the intervals and then translate this to an assumption. Okay. The part that we're in our research group that we have developed here, right, which is semi-automatic, is that part of CSP. But the idea is that, well, very soon we are going to have that approach automatically implemented. So in that case, when you get those intervals, so we treat those equations to put in the format of a CSP problem, right, as I have described it here. And then we are use a solver from IBM. I don't recognize now the name of the solver, but then we give that formula to the IBM solver as a CSP problem in order to tell us what to be the contracted area, right, that a given variable can assume in the code. So to answer your question, it's semi-automatic, this approach, but we are working on it right now to make it fully automatic. Okay.
Yeah.
So are you limited to intervals or?
Yeah, right now we have just applied this for using intervals. We have not investigated all the abstract domains, octagons, polyhedrals. That's a research area that could be further exploited.
Okay, sure, thanks.
Yeah. Deepak, did I answer your question?
Yes.
Yeah,
okay.
Yeah, Lucas. Yeah, thank you. Yeah.
Okay, good. Yeah, so then here's some experimental results of this approach. As you can see here, we have the SMT, right? Without contractor and with contractor. In a quick inspection here in this table, you can see, well, there are a number of cases that the SMT gives a timeout, right? Without the contractor. And then when it does not give a timeout, so you have a considerable verification time here. We could also reduce the length of the interval to optimize, right? Yes, Tabashi, yes, we could. That's the idea of the contractor. Okay, that's the idea of the contractor. It's essentially to reduce that's the size of the interval, the length of the interval. And then you can see, well, Lucas, abstract interpretation, well, is available, that technique, for quite some time, right? And then why people have not applied contractors via SSP, right, to optimize those intervals? That's a good question. I don't know. But well, we are maybe.
Yes, sir, I got it. I mean, we could
Yeah.
also, I mean, reduce the size of the interval to
Yes.
optimize. Yeah.
Okay, good. Yeah, then as you can see here, look, the rate of the state space reduction with contractors. So in some cases, in this case here, 100%, right, of the state space. Other case, 91%. And if I use just the contractor, okay, without BMC, right, because as you have seen, we have used abstract interpretation, compute intervals, then convert this to a CSP problem, and then with the CSP problem, we apply the contractors to reduce the intervals, and then you give this to a BMC engine, okay? So if you just use contractors, we can determine whether the verification is successful or not, just in 4 cases, okay? And also, if you use just abstract interpretation, so we have used FramaC, which is a very popular abstract interpretation framework. So just in 3 cases of these benchmarks, FramaC could determine whether the verification is successful or not. The other case here, they gave unknown. And then you can say, Lucas, you deploy here a solver, CSP solver, right? How much is the performance of that solver? So if you can see here, right, it's pretty fast to reduce, right? Or as you can say in the words here, to optimize those intervals, right? So that's in the scale of microseconds here. I think we have just 1 case that it took 12 seconds, right? But with the original BMC, it gave timeout. And then with that CSP solver, so it gave 12 seconds to reduce the size of the length of the interval, right? And then when you give this to BMC, so that was pretty fast. Okay, we took less than 1 second. So this research that we're doing in terms of CSP in software verification is something that's very active now in our research group. Okay, so very soon, as I have mentioned, very soon we're going to release an implementation of this technique. We have released a technical report about the proposed method, right? And then we're now working on the implementation of this technique. And everything here is about BMC combined with CSP, right? We have also developed here a k-induction proof rule, right? In our k-induction, it's an incremental verification approach that we check 3 cases, okay? We check the case of the base case. Base case is essentially plain BMC. You want to find count examples up to the bound K. Okay, and then the second step, so if you find the count example, we stop the verification procedure. If not, we go to the forward condition. And then the forward condition, what to do is essentially we check if all loops were unrolled enough. How do you do that, Lucas? We actually build what we call as unwinding assertion. What's the unwinding assertion? We essentially get the condition of the loop, right? And then you check if, well, if that condition was actually met, right? If the loop was fully unrolled. That's the only thing that you do in the forward condition. And then the last step is the inductive step, or step case, as you call in the literature. And then this here is a bit more tricky because, well, we have to get the loop. And then with the loop, we have to over-approximate the loop. And how do you over-approximate the loop? We assign no deterministic values to the variables that participate in the loop, right? And then when we over-approximate the loop, you have to come up with loop invariants, okay? Because the device is going to be tricky for the k-induction to work, right? So then we have developed, as I have mentioned before, we have developed an abstract domain just for intervals, and those intervals just for integer variables. And also, we have developed a value set analysis for pointers, okay? And again, let me show you one illustrative example here. So let me go back here to this example of value set. As you can see here, look, we have three variables, x, y, and z. And then R1 is going to get the address of x. R2 is going to get the address of y. And then I have a loop. While z is greater than 0. And then see, z is no deterministic. Okay. And what I'm doing here, so I create that temporary variable that will assign R1 to that temporary. And then we get R2 in R1, then PR2, and then the current Z. And then at the end, we're going to check if R1, if the reference of that point R1 is equal to X or equal to Y, which are the two possibilities here, right? If apply just the k-induction without producing variants, as I have mentioned to you, so let me get this example, SMT, value set minus k-induction. SMT will be unable to prove by induction that this assert here that property holds, right? So we have a bound here in the incremental check that you can put actually even unlimited k steps, but that's not going to work. Because why it does not work? Because if you look at the program here, right? Look, Z is no deterministic here. And then when I over approximate this loop, right? So, well, that's not going to tell me much about that assert statement that I have after that loop, right? And then what I have to do, there is an option that we perform value set analysis. So let me get here help. You can see here, look, interval analysis, enable interval analysis for integer variables and add assumes to the program. And value add max value sets. What this option here means? It means that we're going to get a pointer. And for that pointer, we're going to check which objects the pointer points to. Okay. And then give the object that the pointer points to, we add that as an assume in the code. If you go back here to our run example, right? So we have R1 that points to the object X and R2 that points to object Y. Okay. And then, well, we can see here that we're actually changing, right? So now R1 points to Y, R2 points to X, right? So then you change the object that the pointers point to. And then when you do that value set analysis for pointers, so we're going to detect, okay, so R1 can point either to X or to Y. And the same holds for R2, right? And then if you add these here, this option, add max value sets, and then I can say, well, now it's verification successful, right? So it's quite important. When you do the k-induction, you need to have invariants in the program, right? So that you can prove by induction that the property holds for any value of k to the bound k of the program. And then from our experience, use here k-induction with invariant inference. So, well, it helps us quite a lot to prove many more programs than plain BMC, right? And then by the k-induction itself, when we bring k-induction and invariant inference. I have also played here, so we have implementation for intervals, okay, in our verification framework. But for octagons and convex polyhedral, so we don't have an implementation, but we have abstract interpretation frameworks like PAGAI, PIPS, which they provide invariants in octagons and as convex polyhedral. And all those invariants, they help quite a lot when you do induction of programs. Okay, that was our experience exploiting these techniques, that research area. So k-induction with the invariant inference can prove many more programs when the invariant generation is enabled. Okay, good. So let me show you some results. Okay, here we have the SVComp, the software verification competition, okay, which runs annually since 2012. So that's the result of the last edition, that was 2021. Right now, We are just preparing for SVComp 2022. But there is a very important category in SVComp, that's reach safety. So you want to check the reachability of a bad state in the program. So we have nearly 5,000 benchmarks in this category, right? With the maximum score of 7,844. And then in this particular example, in this particular category, which is quite important in SVComp, so you achieve the 4th place. Use gain induction invariant inference that I have presented to you. We didn't apply yet CSP here in SVComp, okay? And then we're very close here to the blue one, that PESCO, right? We have CPA checkers, the second one. And VSS-IARCS, I think VSS-IARCS developing Ninja. So I think your colleagues in Ninja did a very good job in SVComp. VSS-IARCS, if I remember well, so that's developing Ninja, that tool. And if you compare here another the very famous tool, that's CBMC. So I think CBMC is the red one, so you can see the difference in performance. CBMC applies plain BMC here to that particular category, right? So you can see that gain induction invariance is powerful, and VSS-IARCS, that's developing Ninja. I think the colleagues also use gain induction invariant inference, but I believe they do a better job than us in terms of invariant inference here. Okay. That's another category here that's I think it's quite important. This one that's from Amazon Web Service. So you know that Amazon has a very strong group in automated reasoning. So they have provided benchmarks from real world applications to SVComp. So they have a category that's dedicated to Amazon Web Service. And then here in this particular category, so ESPMC got the 2nd place, right? So the 1st place here was SMAC. SMAC also use some sort of BMC. They built on top of LLVM, and I think they use Boogie. I have a question here. So can you induct on any number of variables? In principle, yes, the Bashish. In principle, yes, but as I have mentioned, so the proof depends essentially on the loop invariants that you can come up. Okay.
So is the proof related to a stronger version of mathematical induction?
Yeah.
Oh,
Yes.
Yeah.
Yes. And then you can see also here again, compared to CBMC, right, with the that's used by Amazon. It's the main verification platform used at Amazon, how they perform it on those benchmarks. I think another tool also here that did relatively well, I think it's Symbiotic, right? Symbiotic is based on top of CLI. I think everyone knows CLI, right? That does path-based symbolic execution. And what's the difference between Symbiotic and CLI is that Symbiotic, they do program slicing. So they have a very good implementation of program slicing that they can achieve even better results than CLI. Okay, good. So that's about verification, right? About SVComp. I'd like to tell you, I have more, I think, 50 minutes here. I'd like to tell you a little bit more about what you do in terms of software testing, which is also another important area. So you also use BMC for bug finding and code coverage. And how it works, we get the program, C or Java, right? And then translate these to an intermediate representation. And then we add safety checks for errors, like for example, for memory safety, for array out of bounds, use of the free, and so on. And also add checks for coverage. Okay, I want to obtain instruction coverage, branch coverage, decision coverage. Then we symbolically execute that intermediate representation to produce an SSA, right? You can see that it's very similar, right, to what I have described in terms of BMC. But the main point here is in the instrumentation that we perform in the program. Then you translate this SSA into a logical formula. And here comes one difference when you apply BMC. We are going to solve the formula iteratively to cover errors and goals, right? So you check each error and each goal in the program. And then we call the solver several times here in this case. And then we interpret the solution. Once you get a counterexample, right, from the so we interpret the solution to figure out the input conditions. And then you split those input conditions as a test case. Okay, so you have a format. We create those test cases as an XML file, right? And then you can give this to a test validator, those inputs translated as a test case in XML to be checked by that validator. Lucas, do you also use popular unit test frameworks? Yes, we use, for example, say C-Unit, JUnit, Mockito, right? You can actually get those input conditions and translate to some unit test framework. Okay, how it works in practice. So let's see this code here. That's quite simple, right? To have that if, I have the input X, and if is greater or equal than 10, so I go to that branch, otherwise I go to the else, and then call function B. Okay, so then I start here our initial state A with the variable X, which is a non-deterministic input. Okay, and then I build here the path constraints, right? So I have the path that X is greater or equal than 10, and the path that X is smaller than 10. Okay, and then from these two paths, if I get the path of X greater or equal than 10, so I have also the path that X is smaller than 100, and the path that X is greater or equal than 100, right? So you can see that to build a path constraint here. And then also build that path constraint, right? So if you want to reach a particular vulnerability in the code, so then you can formulate these as a satisfiability check for the solver. And then this particular case, so for me to reach the vulnerable code, the solver here is going to tell me, oh, look, X99 is a value that meets, right, the constraints that you have for that path. Okay, and that works for both, right? When I have the error that we add as a safety check in the program, and also the cover, right? I mean, when we want to check for coverage, for example, we add labels to the program for each basic block. And then we check if that label is reachable. And then to check if that label is reachable, so again, we build the path constraint, and then the solver is going to tell me if there is a value that satisfies the constraint. Okay, that's quite simple. They say, well, look, that's very simple, right? What I've done. How do you perform with the state of the art? So again, the last edition of the competition, the test comp. So we participated here in a category that's called cover error. Okay, what's the goal of the cover error? So you have the program and the test specification. Find me a test case that covers the error. That's the problem that we solve here in the cover error category. And then here we have implemented this technique here as a tool that's called fuse BMC. Why fuse, Lucas? Because, well, fuse comes from fuzzing and symbolic execution. And BMC, as you already know, right? So you can see that we not only do BMC, but also do fuzzing. We combine both techniques. But Lucas, what's the role of BMC here? What's the relevance of BMC? I can tell you that to get these results, the BMC technique was responsible for 8%, 80, of the outcome of the competition. And 20% was the fuzzing part. Okay. And then Fuse BMC was by far the best software testing tool to that particular problem, right? You can see here other famous tools. That's CLI, right? So CLI is quite famous. So you can see the position of CLI in the software testing competition for the cover error, right? And then we have some other candidates here that are quite strong. VeriFuzz. I think VeriFuzz is also developing India. I think India has a very good representative in software verification testing. So that's VeriFuzz. So they did also very well in the cover error. And they also use fuzzing and BMC. But what's the difference? The verification engine that they use is CBMC and not SBMC here, right? And they might have some other difference here that I don't remember here to mention to you. Okay, but then Fuse BMC in general, so we got 3 awards. First place in cover error, second place in the overall, and third place the energy consumption. So in terms of, we have seen that BMC is not only good to find bugs, but also to save energy. So the organizer of a test comp and SV comp, they check the amount of energy that each verifier takes to solve the verification problems or the testing problems, right? Good. So then in terms of achievements of this work, so I started work in this area in my PhD in Southampton from 2008 to 2011. And then I received in 2011 the Distinguished Paper Award at ICSI. And that paper, I have described verification approach for multi-threaded programs based on symbolic execution and SMT solving, okay? So since 2012, with the first edition of the competition of SVComp, so we started participated, and the last 2-3 years also we had the test comp, the software testing competition, and then over those years from 2012 and 2021, so we accumulated 28 awards in those competitions, and then our strength, I would say that's about bug finding and cover error, okay? We also currently have Intel that deploys ESPMC in production as one of its verification engine for verifying firmware in C. So we have an active collaboration with Intel. So Intel funds one of my PhD students, that's Rafael Menezes, and then we are collaborating, integrating, giving support to run ESPMC to verify firmware in C at Intel. And in the past, we also had collaboration with Nokia to verify telecommunication software written in C++, and Nokia could find a couple of security vulnerabilities in production code, which were later confirmed and fixed by the developers. These are the achievements, and then conclusions. So we have seen that SAT and SMT-based soft model check is a competitive method to verify programs. So our group is very active in this area. And what we're doing right now, we are actually extending this verification framework now to verify neural networks. So we have a project that's called Encore that want to do verification and also explainability of AI models. And then if you go to my webpage, you can see a recent report that we're deploying SMT-based model checking to verify quantized neural networks. Right? Why quantize neural networks? Because, well, when you try to deploy a neural network in a physical hardware, right? So you have to specify the arithmetic, if it's going to be fixed point, floating point, and then if it's fixed point, so what's the influence of the integer and fractional bits, right, in terms of the safety of the neural network? So you have a technical report of almost 50 pages where you describe how you have extended SMT-based model checking for verify quantized neural networks. We can handle a variety of properties, right, in programs, including memory safety, reachability, and also concurrency. So I have not covered concurrency here, but I'm going to give a pointer to one of my MSc courses that I teach in Manchester, where you cover extensively concurrency. We support several types of verification strategies, which include increment verification, k-induction, termination, invariant inference. And then the invariant inference, as I have mentioned, we just support the abstract domain based on intervals. And so the tools, well, we have a couple of customers that they use the tools that to develop to find security vulnerabilities in large-scale software systems. And then we have a couple of research grants, okay, that we have that are running right now in Manchester. We have Scotch, which is funded by IPSRC and ARM. We are developing verification tools for capability hardware. So ARM is going to release a new platform that's called Morello, which they intend to solve the security problems, right, by adding what they call as capability pointers, right? So they add additional information to the pointers in order to detect when we have an out-of-bounds access in the memory. So we have in core that we are doing verification and interpretability of AI models, okay? And Elegant, that's more related to the verification of IoT software. And Soteria, we are also working with people from the web service domain. So they are porting the JVM, the Java Virtual Machine, for the Morello platform. I use the Cherry C++ and does not have any exploitable in the code. Okay. Now I'd like to make some propaganda here. So we have the web page of the SMT project that I have presented here. Okay. We have also the GitHub link that I have provided here. Let me show you here the web page of our group. So we have a group here in Manchester that's called Systems and Software Security Research Group that I lead. As I have mentioned, we have a couple of research grants related to systems and software security. We are always looking for PhD students, for postdocs, and even if you already hold a permanent position in India, so if you want to spend your sabbatical here in Manchester, so please get in contact here so we can arrange a sabbatical for you. So the group's quite active. We are looking for people to collaborate. And then these are the research areas that we have in this group. So we have people from cryptography, network and distributed system security, data and identity privacy. My research area, that's system and software verification, and also system governance. Okay, that's the web page of our research group. So if you are interested in pursuing a PhD or apply for a postdoc or sabbatical, please get in contact with us. And I also run an MSc course in software security. Okay, so that's the link of the software security course. So all the technology that I have described here, I describe in further details in this course of software security. So you have all the videos, the slides, coursework, quiz, right, available here. So with short videos that you can watch, right? For example, I have mentioned about concurrency. So there is one particular week that just focus here on communication models for concurrent programs, the laser exploration, sequentialization methods, schedule recording, and so on. If you want to use this course here in your research institute, so again, get in contact. I can give you the sources of the slides, coursework, and so on for you, so that you can reuse these in your research institute. Okay. I think that's all from me. So if you have questions, so I took 1 hour exactly, as promised.
Yeah, thanks, Lucas, for a very interesting talk. Yeah, we certainly have time for questions. So I would request people to unmute themselves if they have any questions and ask. So yeah, so Lucas, I'll begin with one. So you spoke about towards the end. You said that you've done some work on quantized neural networks.
Okay, yeah.
And so I believe the challenges there are very different. And so are some of these techniques that you spoke about, they're also applicable and useful there? Or,
Yeah, that's quite interesting question. Kumar. So let me show you the technical report that I have mentioned to you. Let me go to my web page here. And then I can show you some of the techniques, how they apply for quantized neural networks. So let me show you some graphs here. Can you see my screen?
Yeah, yes.
Okay, good. So let me show you.
Screen, that will be even.
Yeah. So I increase here. So let me. Yeah, I'm increasing here.
Yeah, this is fine.
That's better. So let me show you the graphs that I have here. First of all, we evaluate the SMT solvers, right? So if you get our verification platform, we have 6 or 7 SMT solvers available, right? I can even just give you a quick overview here over the code. If you go to SMC, then you go to sources, then you go to solvers. You can see that we have, look, BitBootstrap, Lecto, CVC4, MEFSAT, IARCS, Z3, and even such solvers like Minisat. When you want to integrate a new SMT solver, here is quite straightforward. We have a layer that we have the common SMT operations, and then there are declared as virtual methods, right? And then when you want to plug that new SMT solver, we essentially implement that virtual method with the functions that are available with the SMT solver. And then we start in this work of the quantized neural network, evaluating the SMT solvers that we have available. And then for quantized neural networks, we realized that the ICs was the best SMT solver that we have available in the back end to solve the verification conditions from quantized neural networks. So we started the evaluation of the SMT solvers, okay? And then comes here the techniques that I have described here. So we have constant propagation. Constant propagation for neural nets does not make any sense here. Why does it happen, Lucas? Because the inputs that you consider for the neural net, they are symbolic. And then there's not much constant that you can propagate here for neural nets. Okay, so there's a comment here, but it's unrelated. So I'm going to answer soon that comment. So constant propagation has no effect. Okay, slicing. Oh, look, we implement slice. What's the idea of slicing? So you get the property, and then we're going to check which assignments contribute to checking a given property. And then those assignments that don't contribute, we simply eliminate. For neural nets, that was quite useful, right? So slicing gave better results in our case, right? So if you disable the slicing, the results become even worse. Incremental SMT solving didn't help much. As you can see here, when you enable the incremental SMT solving, the SMT solver they become much slower. And then for quantize and neural networks, that was not a good idea. Although you can simplify a lot the model, but the current implementation of the push and pop mechanism, the SMT solvers, they didn't provide good results for that type of verification. Okay, and and then evaluate here also the interval analysis. We have our own interval analysis based on integers. In our case, so it didn't help much, right? But look, if you deploy from a C, which can infer invariants based not only on intervals, but also octagons and polyhedra, right? For quantized neural networks from a C did a very good job to reduce the state space exploration, right? So then in this report, he'll evaluate all these techniques, how they work for quantized neural networks, okay? Then here we play with the resolution because, well, we have the activation function in neural nets that have the ReLU, sigmode, turn age, right? And then especially, for example, the case for sigmode, we have real numbers. And then if the real number, so you want to evaluate the resolution, right? If you decrease the resolution, how the verification results here, what do you get in terms of verification results? So then you have a set of experiments that you did in this technical report that's right now under review at the ACM transactions on embedded computing systems. So I'm not going to further details, so you can check on my web page and then see all the experiments that we have done, right? And more importantly, okay, Lucas, how here, when you change the number of bits and how the verification time here is going to behave, right, when you change the number of bits, but more important, how it performs against others verification tools for neural networks, right? So then you have compared with Marabou, that's developed in Stanford, and NeuroPhi. If you take a look here with Marabou, which also deploys SMT solving, is an SMT-based verification approach. So our method here was much better considering the Akashu benchmark, which is a standard benchmark that people use in deep neural networks. For NeuroPhi, so NeuroPhi is quite efficient. NeuroPhi does not support quantized neural networks. So here we have just verified neural networks without quantization. But NeuroPhi is quite competitive with our approach as well, right? So then what I have presented here to you today, we have done some extensions to adapt these to verify quantized neural nets. And then if you compare to the state of the art, it's also a competitive approach, okay? Good, so I think I have two questions here. So, sir, what's the level of verification feasible in code heavy floating point operations? Is all verification which can be done for integers operation be done for floating points also? Well, I can tell you, Joy, that when we do the floating point computation, then we enable the theory of floating point of the SMT solvers, it is slower than if you do this with just integers. It is slower. In our verification framework, we have built a common layer, okay, that we implement the IEEE 754 standard, that's about the floating point. And then you plug any SMT solver but then with our layer, right? So we can actually convert the floating point operation to a bit vector. And then you use the bool actor. And then that's another paper that we have published. So we have shown that, well, we outperform others solvers that they have a built-in floating point API. But overall, when you have a program with floating point, it's much harder to verify than a program with integers only.
Excuse me, sir.
Yeah.
So I had a vague question in the comment section. I mean, somewhat vague, but I feel that
Tashish, so I think you put a question here. Sir, is it somewhat related to the fact that if there are a finite number of discontinuous, then you can approximate a good function? Yes, that's correct. That's correct, Tabashish.
yes, sir. Yes, sir. Thank you, sir.
Yeah. And Ajoy, did I answer your question?
So,
I think so, right? He didn't
yes, sir. Yes.
respond.
Oh,
Oh,
sorry,
yes,
sir.
he said yes. Yeah, Ajoy. Okay, good. Do you have further questions?
Yeah, so once again, it's me. So the intervals that you were generating, you said that CSP, you pose it as a CSP problem, and then so what are the challenges when you move to other domains? Is it you can still pose it as a CSP problem and do some synthesis, or what is it that you can do there?
Yeah, we do have abstract interpretation frameworks available to compute abstract domains for octagons and polyhedra, right? But for CSP is a good question. It's a research question that I don't know the answer. How difficult that would be to extend these to other domains. For intervals, it's straightforward. And then what I'm trying to do, Kumar, right now is to fully automate the approach. Based that is straightforward, even so it gives some work to fully automate the technique. But it's a research question. I don't know the answer. Probably it's going to be harder.
Okay, sure, thanks.
Good. So again, if you are interested in doing a PhD, postdoc, or sabbatical in Manchester, please get in contact. You'll be very excited to host people from formal verification here.
So Lucas, one question on, so you said you'll also handle concurrent programs.
Mm-hmm.
And are you all able to, find invariants and prove things there, or is it just bounded?
It's just bounded the Deepak. Okay. I think it's a hard problem as well to, compute intervals for the program variables for concurrent programs. I think there are some papers that they already do that kind of stuff, but use induction with those invariants to prove the correctness of concurrent programs, I have not seen. I have not seen yet. If there is some method available, I don't know how scalable and also in terms of soundness and completeness, right, of the method.
Oh, so,
but the maximum that I have seen is just use the intervals and then use the PMC, right? And then in this case, Deepak, let me correct what I said. What they have done is there is a sequentialization method that you get a concurrent program, and then you convert this concurrent program that's no deterministic sequential program. That's the law reps technique. Right. I think Akash Law is even from India as well. So that work on that technique. So then once you get this no deterministic sequentialized program, so I have seen people that, well, now you can use all techniques, right, of invariant inference, chain induction in order to prove the correctness. But doing this in the concurrent program, no, not yet. I have not seen.
You mean doing it directly on the concurrent program without sequentializing it?
Yeah, the sequentialization. On the method that was developed by one of your colleagues, Akash Lau. Yeah,
Yeah, thanks, Lucas. Yeah.
good.
Yeah. So if there are no further questions, maybe we can unmute ourselves and thank Lucas for the talk.
Yeah, thank you.
Thank you.
Thank you, Lucas.
It was a pleasure. It was a pleasure. So then we should also schedule one talk from you guys in Manchester as well. Kumar, keep
Yeah,
in
yeah,
contact,
certainly.
and then let's arrange a talk from you guys in Manchester. I'll be very
Certainly,
happy to